Hey everybody. Well, we're on 9.8, which is talking about something called a power series. 9.7, we actually already learned about power series. So let's kind of review what we talked about. What we talked about was that way long ago, we used to learn how to write the equation of a tangent line, right? And we could use this tangent line to approximate values near the point of tangency. And we talked about how we could rewrite this in using a different notation and then use function notation, right? Let's pretend x1 is c, right? x1 is c, that's where we want to do it. Then y1 is f of c, m is f prime of c, and then this would be x minus c. And then, so this was like maybe a Taylor one, and then we would say, hey, the Maclaurin one, c is 0, so in which case we'd get f of 0 plus f prime of 0 times x minus 0. And in this case that we're looking at over here for e to the x, this would just be e to the 0 plus the derivative of e is also e, so e to the 0 times x, and we would get 1 plus x, right? So that the first degree polynomial was just 1 plus x, was basically a tangent line. The next degree polynomial is we would add the second derivative. Hey, Miss Miranda, how's it going? We had a second derivative at 0, and then we multiply that by x minus c squared, and we divide by 2 factorial. So in this case, that is getting the same thing, but then adding again f double prime of 0 is still 1 times x squared over 2 factorial. And then if we keep doing this, we would get, let me go and do this so we can actually see what's going on. So that one would be this, and then we keep adding on. We add that one, we add the third derivative over 3 factorial, and this, and basically what we're doing is we're approximating e to the x, right? And so you can see those are the approximations of e to the x, and the more terms we add, the closer of approximation we get. Right, the higher degree of the polynomial, the better the approximation. So then the next question becomes, well, what if I used an infinite amount of terms, right? That's kind of what calculus has been about this whole time, is either infinitely big things or infinitesimally small things, right? So, well, what if I just kept adding terms, right? So that's what this piece down here is I'm just going to keep adding on terms and adding and adding and adding. The nth term is given here, right? This is how I'd find the nth term, but then I just keep adding forever and ever. Then what's cool about that is that would actually give me, right? Notice how we're using the equal sign. That would actually give me the exact value of e to the x, right? And so that's called a power series, is coming up with the summation notation, right, for the function that would give me e to the x, right? So let's talk about what a power series actually is, right? So I've erased some things on here, so be careful. The regular series that we've already learned look like this, right? And we would basically just get a1, right? You plug in 1, you get a1, and then we'd plug in 2, we'd get a2, and then we'd plug in 3, and we'd get a3. And you plug in 4, and you would get a4, and so on and so forth, right? With the power series, what we're doing is we're adding a variable to that, right? So we're adding an x to the nth power. Okay, so we're going to add an x to the nth power to this. I'll go ahead and do it like this. And so what that basically comes is, oh shoot, I messed this up, because it should be, we start at 0, right? So it should be a to the 0 plus a to the 1. When I plug in 0 to the x, I get x to the 0, which is 1. When I plug in 1 to the x, I get x to the 1. When I plug in 2, I get x squared, x to the third, x to the fourth, plus plus a to the n, x to the n, right? There's the nth term again, and then I keep adding after that. So it's very similar to an infinite series, except now we have a variable in there, right? So that's basically a power series centered at 0. If we want to center it at some other number that's not 0, then basically instead of writing x, we're just writing x minus c, everywhere x used to be, it's an x minus c, right? And that basically just shifts it over c units to wherever we want it. All right, so the big point here is that a power series, which is those Taylor series that we looked at last in Maclaurin series, a power series is the same as just a numerical series, except there's a variable in there, right? So let's look at some examples of some power series, right? So again, we have this infinite sum notation, meaning we're going to be adding a bunch of things, of x to the n divided by n factorial, right? In the previous chapter, we would have learned about 1 over n factorial. Now we're talking about x to the n over n factorial. And so you just plug in 0, plug in 1, plug in 2, and you're going to get this, right? You're going to get that, that series that looks just like that. Here's another example, right? We're summing up. Again, here's an alternating power series because of this. We're taking x plus 1 to the n power, right? So you plug in 0, and you just get 1. Plug in 2, you get this. Plug in 3, you get that. Plug in 4, you get that. And you add them all together. All right, and then here's that one was centered at -1 because instead of x minus c, we wrote x minus -1, which gave us that x plus 1. The next one is centered at 1, right? So everywhere you can see here that it says x minus 1, which means it's centered at 1. Again, we're just plugging in 1, 2, 3, adding them all up, and we're getting a power series, right? So just like with normal series, what we want to do is we want to find a radius and interval of convergence, or we want to find, does it converge, right? That's the question. What is it going to converge? For the other ones, for just a normal series, we ask, does it converge or diverge? If we're dealing with a power series, then we're going to be dealing with a radius and interval of convergence, meaning it's going to depend on what x values we use, right? So first thing to think about is, because this is an infinite series, it goes on forever, it can exactly give us the exact value for a function of x. So we can actually write f of x equals some power series like this, right? And something important to note is every power series will converge at its center, because remember, that center is the c. As we talked about last session, the c is the point of tangency. It's the point that our function must be equal to our approximation, right? So every single power series must converge at its center. Wherever it's centered at, it will converge there, right? So there's three possibilities with convergence. One of the possibilities is that the only place it converges is at C. The only place where they're actually equal is at C. Another one is that there exists some number r, what's called the radius of convergence. R must be positive, so that the series converges absolutely in that interval. We'll talk about this more. This notation's kind of funky, but if you can look at this and understand it, that's great. And then sometimes the series just converges for every x value, right? It will always converge. There's no radius. The radius is infinity. And again, that radius, that r, is called the radius of convergence. And so, more important information here. If it only converges at C, right? If it's case 1 up there, the radius is called 0. And if it converges for all x, case 3 up there, then we say the radius is infinity. All right, let's look at some examples of how to do this, right? So let's start with this one. We're given this power series, right? And we're asked to determine the radius of convergence. All right, so basically we're going to use one of our convergence tests. And the convergence test that we always want to use on this is going to be the ratio test, right? So almost always we're going to use the ratio test, right? And you'll see why in a second. So if you remember, the ratio test said that we're going to take the limit as n goes to infinity of the absolute value of a n plus 1 divided by a n, and that it converges if it's less than 1, not less than 0, less than 1. Right? So we're going to use that. So basically, what we have to do is plug in n plus 1 and then divide by the normal one, right? So we're going to get limit as n goes to infinity. We're going to plug in n plus 1. We're going to get n plus 1 factorial times x to the n plus 1, right? And we're going to divide that by the original function, which is n factorial times x to the n. And we need to evaluate this limit. And what we're trying to show, sorry, this is important here, is we need to show when is this less than 1, right? We're trying to find for what x values is this less than 1. So we're going to do our normal tricks. And I did forget one other thing. I forgot the absolute value symbols, right? Don't forget that. That's important. We're going to do our normal tricks, right? We're going to take a limit as n goes to infinity. We're going to write this as n plus 1 times n factorial. We're going to write this as x to the n times x to the 1. And we're going to divide by n factorial times x to the n. And we're still trying to show, is this less than 1? Right? So let's do our cancellations. The x to the n is going to cancel x to the n factorial is going to cancel n factorial. Ooh, I forgot it again. Don't forget our absolute values. Those are important. And we're going to be left with the limit as n goes to infinity. Write those absolute values first, so don't forget them, of n plus 1 times x. And we want to know, when is this less than 1? So the thing here is, because this limit is dealing with as n goes to infinity, this x doesn't really matter, right? The x is not going to change in terms of n. So the x is a kind of like a constant in this, right? It doesn't have any effect. Like the n does not affect it at all. So we could rewrite this as the absolute value of x. We're going to like factor that x out to the outside of the limit. And all we're left with now is n plus 1. And we're trying to show, well, when is this less than 1? Well, the limit as n goes to infinity of n plus 1 is, this is infinity, right? And so we're asking, okay, well, when is x times infinity less than 1? And the answer is never, right? This is never true. So this is the point where there is no radius of convergence. The radius of convergence is 0 because we got an infinite limit there, right? The limit did not exist. So the radius of convergence is 0. The only place that it converges is at 0, at the point of tangency. Right? Let's look at another one. We're dealing with this, right? So again, we're going to apply the ratio test to find the radius of convergence. We're going to take the limit as n goes to infinity, absolute value of 3x minus 2 to the n plus 1, right? The top one is n plus 1, and we're divide by 3x minus 2 to the n. And let's go and start by canceling some stuff. Oh, and we're trying to show, when is this less than 1? All right, so we can cancel those 3's, do our normal tricks, which is writing this as x minus 2 to the n times x minus 2 to the 1 over x minus 2 to the n. You still want to know, when is this less than 1? This will cancel with that. And so we'll be left with the limit n goes to infinity, x minus 2 less than 1. Notice how there are no n's, right? So it's kind of like n is 1. The limit as n goes to infinity. If there's no n's there, then we're done taking the limit, and we're left with the absolute value of x minus 2 is less than 1. All right, and like we could solve this absolute value equations, but basically what this tells me is that this number here is our radius of convergence. Right, we would say big R equals 1. And later we'll talk about an interval of convergence. Okay, so right now we're just on radius of convergence, which is going to be r equals 1. You could think about like, well, what is the radius of convergence, which would be basically solving this equation, which you would get x minus 2 is less than 1, and you'd have another one which would be x minus 2 is greater than negative 1, and so you get x equals 2, sorry, x is less than 2, and x is greater than 1. So that would be like, oh, well, here's 1, and here's, sorry, this one should be a 3, right? 2 plus 1, 3. And here's 3. Our interval of convergence is going to be between 1 and 3. And the radius of convergence is 1 because it's centered around 2. And you can see that, you know, the radius going outwards is 1. Right, so we will get into that more later, but there it is for now. Let's do another one. This one has some alternating going on in it, right? We know that because of this. It's going to go plus minus plus minus. Doesn't really affect the ratio test that much. So let's go ahead and take the limit as n goes to infinity. It's important that you don't get lazy on these and like skip steps and just try to do it all in your head, right? It's important to write this stuff down and actually do it, right? So this is going to be negative 1. Remember, for the top one, we're replacing all n's with n plus 1. We're not replacing x's with n plus 1, we're replacing n's with n plus 1. Okay, and divided by 2. It's a good one. It's going to be long, I can tell already. Right? And then we're going to divide that by the original one. Because the original was a fraction, dividing by a fraction is going to be the same as multiplying by a reciprocal. So we're going to go ahead and just write the multiplication by the reciprocal on this step to save us some trouble. And there we go, right? Now we need to clean this up. What the absolute values are going to do is they're going to make it so all the positive, negative pieces go away, right? These aren't going to matter because all those do is change from positive, negative, negative, positive. So those are going to be meaningless. So let's go ahead and do some other stuff. And don't forget that we're trying to show that this is less than 1, right? So we'll take the limit, absolute value of, if I simplify this piece, it's going to be x to the 2n, distribute the 2, you get 2 and 3 here, 2n plus 3 times 2n plus 1 factorial divided by, again, distribute the 2, you're going to get 2n plus 2 plus 1, which is 2n plus 3 factorial. And then over here we have times x to the 2n plus 1. And we're trying to show that this is less than 0. All right, so clean this up a little bit. And we got to use some of these tricks of exponents. All right, let's do it this way. Let's do limit as n goes to infinity. I think it'll work just to break it up like this. X to the 2n times x to the 3. We can leave this as 2n plus 1 factorial. On the bottom, we are going to take out 1. So we're going to 2n plus 3 times 2n plus 2 times 2n plus 1 factorial, right? Notice we're just counting down, times x to the n 2n plus 1. And we're trying to show this is less than, I keep writing 0, it's less than 1, right? If you wrote a 0 up here, please change it to a 1, right? It's less than 1, less than 1. So what's going to cancel is this x to the 2n. Oh, this is, sorry, let's go and simplify this too. It's x to the 2n times x to the 1, right? That's that same property. And then this 2n plus 1 factorial will cancel that 2n plus 1 factorial. And we're going to be left with x to the third. So this, here, let's do this also. This is going to be x to the third divided by x to the 1, which is going to be x squared, right? So on the top, we're going to have x squared divided by 2n plus 3 times 2n plus 2, and that canceled, right? So that's what we're left with. And we're asking, was this less than 1? We can factor out that x squared if we want to. But we don't really need to. We can just think about it. So the limit as n goes to infinity, notice n is on the bottom. So for any fixed value of x, right? Remember x, for this limit, we can kind of treat x as just like a constant, because for this limit, the n is what's changing. So think of x as like a constant. Any constant and divided by infinity is going to give us 0, right? So basically, this is going to be some number divided by infinity, which is 0. So basically, we're going to get 0 for this whole thing is less than 1, right? And so we get the 0 is less than 1, which this is always true, is it not? 0 is always less than 1. What that means is that r is infinity, right? Since this is always true, there are infinite amount of solutions, and the radius of convergence is infinity. Okay. Before we go on to number 5, we need to talk about intervals of convergence and the endpoints. Okay, so we're going to look at this piece down here before we do that example up there. So if we have a radius of convergence and it's finite, right? So it's case number 2, where we actually get a number. We don't get 0 or we don't get infinity. We have no idea what the convergence at the endpoints are, right? All it tells us is like the radius of convergence. And so what we actually have to do is test the endpoints individually. As far as the convergence or divergence for like the intervals, there's these things that could happen down here, right? So you could have a radius of 0. That's the point where it's only converges at the point of tangency. The radius could be infinity, meaning it goes on in both directions forever. Or we could have an interval of convergence where the radius is the distance from the center. And then notice the brackets, right? Open brackets meaning the endpoints aren't included, or where the left endpoint could not be included, but the right endpoint is included, or both endpoints could be included, or any variation of that. So what we have to figure out is like we need to test the endpoints. Okay? So that's what we need to do in example number 5 here, because this one's asking for the interval of convergence, which is different than the radius of convergence that we're looking at there. Okay, so I'm going to do this one real quick and then pause, and we'll make the rest of the video later. All right, so interval of convergence starts the same way, right? We're going to start the exact same way. We are going to we're going to use the ratio test. We're going to take the limit as n goes to infinity of the absolute value, right? And we're going to do the n plus 1. So this is going to be x to the n plus 1 divided by n plus 1. Since it's a fraction, we just multiply by the reciprocal for the nth term, like this. Do some, and we're trying to show this less than 1. Do some of our normal tricks. Right, these x to the n's are going to cancel. And we're going to be left with the limit as n goes to infinity of the absolute value of x, nx over n plus 1. We're trying to show this is less than 1, right? And so again, if it's helpful, we can go ahead and pull out that x, right? Write the absolute value of x on the outside, and then we're taking the limit of n over n plus 1. And the limit of n over n plus 1 is just 1. So basically we have the absolute value of x times 1, which is the absolute value of x, is less than 1. Right? So again, our radius of convergence is 1. If we drew this on a number line, right, the center is 0 because there's nothing here, and our solutions would be all the way up to 1 and negative 1, right? 1 in the radius is 1 in the direction to the right, 1 in the direction to the left. But we haven't figured out the endpoints yet. Like, we don't know if the endpoints converge or not. So we need to check the endpoint. So I need to check when x equals -1, right? So these are x values, right? So I need to check when x is -1. So we come up here to our series and we check, well, if x is -1, then I get this. And I need to check the convergence or divergence of this, right? So what we should recognize is, hey, this is an alternating series, right? So we're testing when x equals -1. This is an alternating series. There's two things I need to show for alternating series. One, I need to show that the limit as n goes to infinity of 1 over n equals 0. That's good. And then I need to show that the next term, the n plus 1 term, is always less than the nth term, which is also good. So this converges, which means -1 is included in my interval, right? Now I need to check 1, right? So this is when x equals 1. We're going from 1 to infinity. If x is 1, I'm replacing that x right there with 1. So it's going to be 1 to the n over n, which 1 to the n is just 1, right? So like I could just write it like this. This is a harmonic series, a harmonic p series, right? That diverges. This one diverges, right? So the right endpoint is not included, and we use like a parenthesis right there, right? So our interval of convergence for this particular one is we would write as the interval of convergence is -1 to 1, right? Including the -1, not including the 1. And that's what this picture is showing as well, right? Okay, I'll be back with more for the other one.
Okay, let's go ahead and generalize something real quick. For the interval of convergence, when you get to the end, if you have this absolute value thing, and you get x minus c is less than some number over here, we're going to call it r, because that's what it is, right? Then when it's in this form, you can easily see like the c here is the center, and the r is the radius of convergence, right? So like whenever you would graph this on a, like when you try to, if you try to create that little graph, you would put c, I mean that's what they're showing you up there, right? You'd put c in the middle, and then you'd move r directions to the right, and you'd move r directions to the r units to the left, and then wherever you end up on those sides is your interval of convergence. But then you would just have to check those points for convergence by themselves, right? Because you have to check them individually. Okay, so let's keep going. Let's do example 6. Again, we're going to use the ratio test to see if it converges, right? So we're going to take the limit as n goes to infinity of the absolute value -1 to the n plus 1 times x plus 1 to the n divided by, n plus 1 divided by 2 to the n plus 1. And instead of dividing by the fraction, we're going to go to multiply by the reciprocal. Like such. And then we'll do all our tricks and whatnot. Remember, all the negatives are going to go away because we're taking the absolute value, so all those little negative pieces are now gone. It doesn't matter what they would have been, it's going to be positive. And we're going to get, this top is going to be x plus 1 to the n times x plus 1 to the 1 over 2 to the n times 2 to the 1. And then over here we're going to have 2 to the n over x plus 1 to the n. That's going to cancel, that's going to cancel, that's going to cancel, that's going to cancel. Oh, and let me not forget that, remember, we're trying to show that this is less than 1, so let's go and start writing that from the beginning, right? We want to show that this is less than 1. And so what are we left with? We're left with the limit as n goes to infinity. We still do need the absolute values here because x could still be positive or negative, but what we can do is like we can still get rid of those negatives because those aren't going to affect it. So we're left here with x plus 1 over 2 when is that less than 1? Again, notice how there's no n's here, right? So if I'm taking the limit as n goes to infinity of something with x in it, the thing with the x is kind of like a constant compared to n. So basically this limit doesn't affect my expression here. This is not quite in the form that I want it. It's not quite in this form up here. But we could just multiply both sides by 2, right? And so we'll get x plus 1 is less than 2. And now we can see that our radius, right, r is 2. And our interval of convergence would be 2 plus 1 and 2 minus 1. Well, that's going to tell us kind of where it is, right? So, sorry, the center is not actually 1, right? The center is -1, right? Because up here it's x minus c. So our radius would take us 2 units to the right, which put us at 1, 2 units to the left, which would put us at -1. And so we're somewhere in there. But we don't know if the endpoints converge or not, right? So we need to check that. So what that means is we're actually going to plug in the endpoints for x, right? These are x values, plug it in for x and see if the resulting infinite series converges or diverges. All right, so where can I do this? I guess I'll do it here and then I'll just have to erase it or something like that. So we're gonna check when, so we're still doing example 6, right? When x equals -3. If x equals -3, then the resulting series is -3 plus 1 is -2 to the n over 2 to the n. This could be rewritten as -1 to the n times -1 to the n times 2 to the n all over 2 to the n, which then could be rewritten as, notice these have the same base. If you multiply them together, you're just going to get 1, right? That's 1. And so we're left with basically 2 to the n over 2 to the n, which is also 1. And so we're taking the series of 1, which is basically 1 plus 1 plus 1 forever. So this is infinity, which means it diverges, which means we are not going to include -3, right? We're going to keep an open bracket there. So the interval of convergence is going to go from -3. And then we have to figure out, well, what about 1, right? So let's check when x equals 1, right? If I plug in 1, we're going to get -1 to the n. 1 plus 1 is 2 to the n over 2 to the n. Again, these are going to cancel, and we're left with -1 to the n, which, you know, basically the first term is 1, next one's -1, plus 1, -1, plus 1, -1. It's tempting to say this converges to 0, but it just it depends on what term you're on, right? If you're on the even term, it's going to be 1. If you're on the if you're on the odd term, it will be 1. If you're on the even term, it will be 0. And it just keeps bouncing back between 1 and 0, 1 and 0. So this one also actually diverges, because it's not like approaching a number, it's just bouncing back and forth. So our interval, right, we're not going to include 1 either, so we're going to put a parenthesis there to say don't include 1 either. Alright, so that's how that one goes. Let me go and delete this stuff. And we'll do the next one. Okay, next example. Find the interval of convergence. Again, we're going to use ratio test, right? We're going to take the limit as n goes to infinity of the absolute value of x to the n plus 1 over n plus 1 squared, and we're going to divide that by just the regular one, which is the same as multiplying by the reciprocal since it's a fraction. And we're trying to show that this is going to be less than 1. Normal tricks, right? It's very repetitive. You have a lot of the same stuff going on. And so what's going to cancel? The x to the n's cancel, and we're left with the limit as n goes to infinity of the absolute value of n squared xn squared over n plus 1 squared. Trying to figure out when is this less than 1. If you want, since x has nothing to do with this limit, we can factor it out like this. And we'll have n squared over n plus 1 squared. And this thing goes to 1, right? So it's basically absolute value of x times 1, which is this absolute value of x. Right, just to make sure we understood that this limit here goes to 1, right? In behavior model, you see n squared over, it will be n squared if you multiply it out. That's going to go to 1. The top and the bottom are the same levels of infinity. And so we can see that our radius is 1, and our center in this case is 0. So if we were going to draw that little number line, we would start at 0, we'd go 1 to the right, and we'd go 1 to the left, and then we'd have to check the endpoints, right? Like, what should I be putting, a bracket or a parenthesis? So let's plug these numbers in, right? Let's plug in -1 to the original, right? So when x equals -1, we're going to get -1 to the n over n squared. I don't know if this is obvious to you or not, but like, so we could, like, this is an alternating p series. It's an alternating series. But you could also do the absolute value test, right? Take the absolute value of this, you're going to get 1 over n squared, which that also converges. So this is like absolutely convergent. You could show that the alternating series converges, and the absolute value converges. So all that's important is that this converges. And then the next one, when we're going to check when x equals +1, then we're getting the sum of 1 to the infinity over n squared, which is the same as 1 over n squared, which is, again, p series, it converges. So in this case, both endpoints converge, right? Or both endpoints are included because we checked the endpoints and it worked, right? Okay, one last thing for this chapter, which is some properties. Let's assume we start with that definition of a p series that's centered at c, right? This is just that same definition right here that we were given in the beginning. It's just like a normal series, but with an x in it, and we're doing x minus c because the center is at c. It's kind of like a horizontal translation that we learned in Algebra 2. And we're saying that it has a radius of convergence that's bigger than 0, meaning it's not just that case of being convergent at the center. Then we can actually take the derivative and the integral of it. And because it's just a polynomial, all we need to use is power rule. So if you notice, if you take the derivative of this thing I've highlighted in yellow, right, this n would come down and make n a to the n times x minus c, and then we would raise it to the n minus 1 power, right? And so that's all this is saying right here, is that the derivative, we can just use power rule to find the derivative of that function of the power series. And it makes our series look a little bit different, but it basically, you can take the derivative and find a rate of change. You can also integrate, right? When we're doing an indefinite integral, we need the c, and then it's like reverse power rule, right? You add 1 to the exponent and you divide by what you get. And so it's it's just power rule applied to a giant series. All right, so we have 3 examples here that we're going to do. We're given this function here, right, which is defined by x to the n over n, the sum, the infinite series of x to the n over n. And we're asked to find the intervals of convergence for each of the following. Oh, so we should talk about up here. So the radius of convergence will be the same when you integrate or differentiate. The only difference might be the endpoints, right? So you only have to check the endpoints to see if they're any different. Okay, so let's do these. So let's find the intervals of convergence for the following. We're going to go ahead and integrate f of x equals x to the n over n. If we integrate this, right, it's going to add 1 to the exponent, right? X to the n plus 1 divided by n plus 1, right? There was already that n down there, so we have another n. And then this is going to give us x to the n times x over, maybe distribute n squared plus n, right? Oh, and I should write the summation there still. Okay, so we need the summation here, and since we're integrating, we need a plus c as well, right? So we need plus c, and typically we write that plus c in the front, right? So the integral of f of x is going to be that, and we're trying to find the interval of convergence, right? So it's, you know, basically the same thing that we did before. We did do this function already, right? Like if we come up here, we did this in example 5, right? So we know the radius is 1. It goes from -1 to 1. So we know we already did this. So let's use the knowledge we already have for the original, right? We did it for the original, and what this theorem up here is saying is that if it, you know, integrating and differentiating only changes might only change the endpoints, but it won't change the radius itself, right? So the radius of convergence here is 1, and the center was, go back up to 5 again, the center was at 0, right? So our interval is somewhere between -1 and 1. We just have to check the endpoints, right? So let's plug in -1, and we're gonna be looking at this series, right? So this is when x equals -1. We're gonna be looking at the series -1 to the n. Let's use this one, over n squared plus n. All right, this is an alternating series. We could show that the limit as n goes to infinity of n squared plus n goes to 0, and we could show that 1 over n plus 1 squared plus n plus 1 is always less than 1 over n squared plus n, right? So that meets all we need to do for alternating series. So this converges, which means we put a bracket there, right? And then let's check the next one. When x equals 1, we would get the sum of 1 over n times n plus 1, which again, this is not alternating, so we got to do something else, but we could just, you know, it's similar to this, which we already wrote, but we could compare to P series and show that, you know, 1 over n squared plus n is always going to be less than 1 over n squared, and since this converges, so does this one, right? Because the smaller, if the big one converges, the little one converges too, and so this converges, which means we can put a bracket on that one as well, right? Okay, let's go to the next one. So the interval of convergence for the integral test was that. And for B, we already did f of x, right? So like we maybe for this one just see example 5. And then for C, we're going to take the derivative, right? So if f of x equals the sum of x squared, x to the n over n, then f prime of x is going to equal the sum of n x to the n minus 1 over n, and those n's will cancel. We'll just get x to the n minus 1, and we want to see if this converges or not, right? So so again, we don't have to recheck using the ratio test, right? We know the radius is 1 because we've already checked that. Like we did that in the beginning. We did that with an example in example 5, and the radius of convergence won't change. That's what they're saying, is the radius of convergence will not change. So the radius is still 1. So we're still just trying to check will it converge at -1 and 1. So if we have, so when x is -1, we get -1 to the n minus 1. which again is just, you know, 1, -1, 1, -1, 1, -1. Just this diverges by oscillation, right? Which means we don't want to include -1. If x equals 1, we have 1 to the n minus 1, which is just 1 plus 1 plus 1 plus 1, which goes to infinity, which also diverges. So we don't want to include that one as well, right? So the interval of convergence here is -1 to 1, not including the endpoints, whereas this one we did include the endpoints, right? So the important thing to remember here is you could use the same test. You could still use ratio tests to like find the radius, but once you've found it for any level of these, right? If you found it for the function, the integral, or the derivative, the radius of convergence will be the same for all of them. All you have to do is check the endpoints. And when you're checking the endpoints, you're using one of those tests that we've been working on for such a long time. All right? Good luck on the practice set.